Hello everybody, welcome to the 10.5 practice day 1, which is solving exponential and logarithmic equations. So let's get going, shall we? Let's take a look at number 1. I hope that you've tried these on your own first. I think it always means a lot more. You try it and then use the video as a resource. So if we take a look at number 1, we have an exponential equation, which means that we could introduce logs on both sides. But before introducing logs, let's consider if we could change both of these bases to be the same number, because usually I find that to be faster. If we take a look at the number 8, can 8 be written as an exponent? Well, we could write 8 as 2 to the third. So what if we did? What if we wrote 8 as 2 to the third, but then the 2x plus 1 is still there, and the 2x plus 1 is going to multiply the 3 that we just put into the problem. So 2 to the 3 times 2x plus 1 is going to equal something else on the other side. Can 16 also be written as a base of 2? Yes, it can. 2 to the 4th is really equal to 16. And then the x minus 6 is still there as well. And it turns out that if your base is the same, that means that your exponents also must be the same. So we can say 3 times 2x plus 1 is going to equal 4 times x minus 6. And if we go ahead and solve this equation, the distributive property, we have 6x plus 3 on this side. We have 4x minus 24 on this side. Move the x's over here, get 2x. Move the 3 over here, get negative 27. That's a terrible 2. If I divide both sides by 2, my final answer is going to be negative 27 halves. But I also said you could have your answer exact or to the nearest thousandths place if it applies. If you divide negative 27 divided by 2, your answer could be negative 13.5 as well. So I would accept either one of those answers. And that is a 2 for those that can't tell. The second example, we again have an exponential equation, and we could introduce logs on both sides. That's always the first thing I think about. But is it possible if instead of logs that we could write both of these numbers as the same base, like we did in number 1? When I see 25, the first thing that pops into my head is 5 squared. So let's try it. The x plus 3 is still there. Try that again. 5 squared, x plus 3. And then this side, can 1 over 125 be written as 5 to a power? Well, I know that 5 cubed is 125. So that means that 5 to the negative third must be the reciprocal. So now both of these bases are the same. So in a similar way, this exponent must equal this one. So 2 times x plus 3 must be equal to negative 3. 2x plus 6 must be equal to negative 3. This pen is terrible right now. 2x equals, subtract the 6 over, negative 9. Divide both by 2. So we have 2 answers we could have. Negative 9 halves is the exact answer, or negative 4.5 as the decimal answer. I would say it's just easier to leave it exact, to be honest, but the decimals are going to come more into play later. Number 3, now this is one that we might actually need logs, because if we take a look at the original equation, which I'll rewrite here for room's sake, 7 to the x equals 24, you can ask yourself if you could write 7 and 24 as the same base, meaning, can I write 24 as 7 to a power? Well, 7 to the first is 7, 7 to the second is 49, so we skip right over 24. So no, it does not seem that we can write it as the same base. So this is when you can apply logs on both sides. You could choose to do log base 7, but if you do log base 7 on both sides, you have to use the change of base formula because you'd eventually have to do log of 24 over log of 7. It works, but it's not the fastest way. I would instead suggest either taking the log of both sides or taking the ln of both sides. In this case, for this first one, I'll choose log. So what we could do is do log of 7 to the x equals log of 24. And because we applied the logs on both sides, we can apply log rules. So that means that the exponent can come down in front. So you'd have x times the log of 7 is equal to the log of 24. And so now if I want to get x by itself, I can divide both sides by log of 7. Now this log in this 7 does not cross out and become 1, because again you assume that this is really log base 10, and this does not equal 1, because 10 to a power 10 to the first does not equal 7. If this was log base 10 of 10, that will become 1, but in this case it does not. So anyway, what we're really going to do is divide both sides by log of 7. And so you could leave your answer in one of two ways. If you leave it exact, I would accept log of 24 over log of 7. This isn't a correct answer. You also in the calculator could actually divide these two things, and if you do that, you would get to the nearest thousandth 1.633. Number 4, I would say, is going to be similar to number 3, except we need to make sure that the exponent is by itself first. So the exponential part of this equation is 3 to the 6 minus x. The first thing we need to do is get that 8 out of there by dividing it. So we'd have 3 to the 6 minus x power equals 40 divided by 8, or 5. You do not necessarily need the parentheses there now. You could just write 3 to the 6 minus x equals 5. Think about if you could write both of these bases as the same base. 3 to the first is 3, 3 to the second is 9, so we skip right over 5, so unfortunately no. Which means we need to either apply log or ln on both sides. Number 3 I did log, so number 4 I'll do ln. It does not matter which one you choose, you will get the same answer in your calculator either way. So if I apply ln on both sides, ln times 3 to the 6 minus x equals ln of 5. What you can do is again bring this exponent down because you applied logs. So we have the exponent of 6 minus x times ln of 3 equals ln of 5. The reason I put parentheses here is because all of this exponent is multiplying ln of 3. My goal is to continue to get the x by itself, so my suggestion would actually be getting rid of ln of 3 and moving it over here. Because these two things are multiplying, I'm going to divide both sides by ln of 3. So we have 6 minus x equals ln of 5 over ln of 3. And if I want to continue getting my x by itself, I'm going to subtract 6 from both sides. So we'd have negative x equals ln of 5 over ln of 3 minus 6. The x, though, is not quite by itself yet because we really have a negative in front of it. So what you're really going to do is divide both sides by negative 1. But on this side, when you divide by a negative 1, the signs of both things flip. So your answer in exact form would be negative ln of 5 over ln of 3 plus 6. This answer is completely acceptable. If you, however, would prefer a decimal because this looks too odd to you, you did negative this divided by this and added 6 in your calculator, your answer to the nearest thousandth would be 4.535. Feel free to check in your calculator as well. So those first equations all started as exponentials. Now the next 4 are going to be starting as logs. So I want to talk about all the different possibilities. When things start as exponents, we either changed the base or we applied logs on both sides. Now that we have logs, we can change them into exponentials because they're inverses, or we could use a lot of different methods. So let's take a look here at number 5. Number 5 I like because both sides we have a log, and if we have the same log with the same base, you assume both of these have base 10. That means that the arguments are also equal, which means that 3x plus 3 must equal x squared minus 1. Because this is squared, we have to factor or solve in some way. So I'm going to move these two over here. 0 equals x squared minus 3x. If I move 3 over by subtracting it, it ends up being minus 4. Is this factorable? Yes, it is. X minus 4, x plus 1. So then I have two possible answers of 4 and negative 1. But it's important to always check your work. So if I take 4 and plug it back in, we're asking ourselves, does log of 3 times 4 plus 13, which would be 15, does log of 15 equal log of 4 squared minus 1? Log of 15 does equal log of 15, so this one is in. Negative 1, if I plug negative 1 on this side, log of 3 times negative 1 plus 3, so that would be log of 0 equals log of negative 1 squared minus 1 would also be log of 0. But here is the annoying part about what it's in blue here. Think about what this means. logs are exponents, and the base of this log is 10. So it's saying 10 to the what is 0. Well, I know that 10 to the 0th is 1, but is 10 to the anything equals 0? Well, 10 to the first is 10. 10 to the 0th is 1. 10 to the negative first is 1/10. So we skip right over this. So both of these statements, there is nothing that makes this true, which means that -1 is out. Even though I got log 0 equals log 0, log of 0 in itself does not make sense, so it makes it cancel out that solution. Number 6, this time we do not have log equaling a log, so we can't just set the arguments equal. So whenever I'm given a log, I think about maybe I can use the inverse and change this to be exponential. So if I do that, let's think about how I could rewrite this as an exponent. The base of this log is 5. The exponent has to be -2 because, again, as I've been saying quite a bit, logs equal exponents, so -2 must be my exponent, and that must equal x. So actually, very quickly, we know that x is equal to 5 to the -2nd, which is really 1/25, because 5 squared is 25, so the negative exponent causes the reciprocal. So you could leave your answer as a fraction, which I would probably suggest you do, but it also is correct if you have the answer as 0.04. Number 7, log of x plus 3 minus 2 equals 4. I would say that number 7 is going to be similar to 6, except it looks like we don't have a base. But really we do. Remember, when you see log, you assume it's base 10. I would suggest getting the log isolated. So the first thing I want to do is move that 2 over. So we're going to have log, technically base 10, of x plus 3 equals 6. And now that we have the log isolated, we can treat it like number 6. We have a log, let's write it as an exponent and see if we can solve. The base of this log is 10, the exponent of this log is 6, and that's equal to x plus 3. So 10 to the 6 is quite large. We got a 1, 2, 3, 4, 5, 6 zeros equals x plus 3. So my final answer, if I subtract my 3 over, is quite a large number. We got our final answer, 1, 2, 3, 4, 5, 7. 999,997. Lastly, number 8, which I would say is similar to 7. This one I put here because I wanted you to remember that you're assuming base 10. If you see ln, you're assuming base e. First thing I would suggest, though, is getting the log or the log base e or ln by itself. So I would add the 1 first. So you'd have 3 ln of 2x equals 9. Then I would continue to isolate the log. I would divide both sides by 3 and get ln of 2x equals 3. Now, if we don't know what to do from here, again, change it. If it's logarithmic, it is an inverse to an exponential equation. So let's change this to an exponential. The base is e technically. So e to the power or the exponent of 3 must equal 2x, or the argument. If I leave my answer exact and divide both sides by 2, my answer for x would be e cubed over 2. If I prefer a decimal rounded to the nearest thousandth, my answer would be 10.043 if I plug that into my calculator. All right, guys, again, feel free to come visit if you have any more questions about this. I hope that this video was helpful for you. Thank you.